Hi, everyone. Thanks for joining. My name's Nathan. I'm one of the marketing managers at Data Science Dojo. We're here with Asim Wahid. He's one of our data scientists as well as an instructor. He's going to be going over coding up a linear regression algorithm from scratch in Python. We're really excited to have him. He is going to be using a coding notebook that we've made available to everyone. I've just posted the link to it in the chat. And if you're on YouTube, I've also posted it there as well. So awesome. Why don't you go ahead?
So, hi everyone. I hope you have a good day, night, wherever you are at. So the purpose of this webinar is going to be slightly, in fact, very technical. I do expect that you would know at some level how a linear regression algorithm works. So you know the basics behind what gradient descent is, you know the basics behind how gradient descent works, the fact that we're optimizing a mathematical function. The goal of this webinar is going to be firstly to teach you the difference between vectorized operations and normal operations in Python and why we do that. The second thing we're going to be dealing with is object-oriented programming in Python, because I've personally noticed that a lot of online courses that teach data science, in fact, even university courses that focus on data science, they don't focus a lot on object-oriented programming. However, in the real world, you do deal with objects all the time. In fact, when you're using the scikit-learn library, or rather any library that you're using, you are going to be playing around with objects. So if this is not something, this webinar and what we're about to do here is not something that will directly almost ever be used in the real world, unless you're working on some sort of really, really complicated research problems where you have to code up mathematical functions yourself. However, it will always be helpful to know these concepts and do this exercise at least once, because once you've done it, then it's there in the back of your mind. And once it's there, then it's very easy for you to debug problems that you run into when you're using scikit-learn or when you're using any library for that matter, because it'll be easier for you to follow an error and figure out what the problem is once you've done all of these implementations from the get-go. So again, the goal over here is to do this extremely complicated, seemingly useless exercise once. But once we've done it, then we have a much stronger skill set that we can use in our day-to-day lives as a data scientist and become a better programmer while we get on with it. So let's just get started. I'll be using some very simple libraries. I'm not importing scikit-learn over here, just some basic NumPy, pandas, and Seaborn. Similarly, because our goal over here is not feature engineering, it's specifically the linear regression algorithm, I'm simply picking up a data set from sklearn, which is the Boston data set. Ideally, we would want to go through an entire exploratory data analysis process in which we figure out what all of these different columns mean, what do they do, what is their correlation with the target variable, which in this case is the price. Simply put, this data set is just using all of these different features to try and predict the price of a certain aspect. So the idea is, and this is not the classification, this is linear regression as a regression itself. Logistic regression was used for classification. Over here, we're sticking to regression. And the reason that I picked this particular data set is because, well, we don't have to do a lot to it. So if we look at the data types, then they're all float 64s. So we don't need to do any sort of data wrangling to convert it to a good data set that we can use. Similarly, it doesn't have any null values. Again, in the real world, your data set will never be this good. But because our goal over here is to simply code up an algorithm from scratch, we're going to stick to a simple data set to which we don't need to do a lot of stuff. So whenever we're working with pure machine learning in the sense that we're coding up algorithms ourselves, it's better to convert our data to NumPy arrays rather than pandas. In fact, if you look at the scikit-learn implementation and you look at the source code of it, even over there, they do convert their pandas data frames into NumPy arrays. And if anybody has any experience with scikit-learn, you will also notice that scikit-learn generally works better with NumPy arrays. Why is that the case? Well, simply put, they're both built for different things. Pandas is better built for data wrangling, data manipulation, running a pivot, running, let's say, a merge, and overall your data cleaning and everything, dealing with data, doing the feature engineering, while NumPy or NumPy, whatever way you want to pronounce it, that's better suited to actually doing linear algebra. And as we get into this more and more, you'll find out that machine learning at the end of the day is just clever use of linear algebra so that you can carry out very complex mathematical functions in just a few lines of code that run very, very efficiently. So let's get into it. Some of the prereqs that I'll first teach you guys is what is a vectorized implementation and why is vectorization so important in Python. And first of all, in case somebody wants a primer on NumPy, a NumPy array or a NumPy array is simply a matrix, right? You can think of it as a list of lists, but a list of lists has very few things that you can do, and essentially they are just lists of lists, while a NumPy array is an actual matrix. And because it's an actual matrix, there's a lot of things that we can pick up from linear algebra that we can simply do directly on NumPy arrays. So if I were to create a list, for example, over here, random list 1 is equal to 1, 2, 3, and then random list 2 is equal to 2, 3, 4. And if I were to do random list 1 plus random list 2, then it just concatenates both the lists. But if I were to do it in a NumPy array, then what we're doing is we're actually adding the values together. So this 2 is simply 1 plus 1, this 3 is 2 plus 1. So each element is just added to each other. And similarly, when we're doing subtraction, each element is subtracted with each other. This is exactly the same way that it works when it comes to linear algebra. And that's exactly the goal over here. We want to be able to implement linear algebra operations very easily in Python, and that's what NumPy allows us to do. Similarly, when we have multiplication, in linear algebra, multiplication is not that simple, right? Where there's many different ways to find the product between two different matrices. The first way is called the Hadamard product. In more simple terms, this is simply element-wise multiplication, and that's done using this star operator. So all this is done is that this has multiplied each element of A with the corresponding element of B. Another thing is the dot product. And what the dot product does is that it multiplies each row of A with the column of B. So this value, the first row, first column is the result of multiplying the first row with the first column. This value is the result of multiplying the first row with the second column, and so on. And that's essentially what a dot product is. Ways to do a dot product. You can do A at B, which is the convention that I'll be using. It's the simplest to use, it's easy to write, and it just works. There's also A dot B, which produces the same result. And then we have NP dot A comma B. So this is just a small primer on NumPy arrays in case anybody didn't remember it. But now let's start to get into actual linear regression and why vectorization is so important. So if we look at the hypothesis of a linear regression, as a reminder, a linear regression equation is just you multiplying a weight with a particular feature or a particular data point. So if your X has multiple different features, then the number of features are the number of weights that you're going to have. So if your X is of, let's actually look at what the shape of our X is. So we have 13 variables there. What's going to happen is that we're going to have a particular M1. So a normal equation of line is y is equal to mx plus c. When we're dealing with linear regression with multiple different variables, we have m1 x1 plus m2 x2 plus m3 x3, all the way in our case to m13 x13. And this is all that this equation is telling us. Again, our goal over here is to convert equations to Python functions and Python statements and how to easily do that. And for that, we need to understand what X represents and how this equation is representing X. So the first thing we need over here is we need a series of thetas. And thetas are going to be of size j. What is size j? Size j is the number of features that we have. And the hypothesis that we're getting, the result that we're getting is for a particular row of data. The number of columns defines how many features you have, and the number of rows define the number of data points that you have. So the first thing we're going to do is we're going to create our weights. And if you look at the weights that I've created, it's just an array of 13 weights, each of which are initialized to 1. Now, imagine if we were to implement this hypothesis function using simple for loops. What are we going to do? We're going to go over each data point in X, which is going to be one row of data. Then we're going to calculate the hypothesis. And the way we're going to do that is we're going to go over each weight and the corresponding data point. We're going to multiply theta by X, and we're going to keep adding it to the hypothesis. That's why I have initialized this as 0. Excuse me, because I can simply add theta into X into it. So if anybody doesn't know what the zip function does, all it does is that, so if I were to show one particular row in X, print data point, and then I'll just put a break here because we only want to see one data point. It's an array. It's an array of size. Let's actually display it. It's an array, and the size of the array is 13, right? And that's exactly what we're doing. When we go over a particular data point, that means we're going over each value one by one, and we're multiplying the theta by X, and we're getting a hypothesis. And for each prediction, we're appending the hypothesis to the prediction. This is the simplest way to implement this function over here. And if we do that, it works. There's no problem with it. But what I want you guys to remember and what I want you guys to understand is that if we were to start implementing for loops for every single data, for every single mathematical formula, we're quickly going to run into problems. Now, the main problem is going to be time. And let me just show you how to do the same thing using a vectorized operation. So again, it's as simple as X dot weights. Why is that? Well, the reason is that our data is of shape M by N, where, let me just, yeah. So if we look at the formula over here, the shape of our data is 506 by 13. The shape of our weights is 13 by 1. And what do we want to do? We want to multiply each row with the weights. That sounds an awful lot like a dot product. If somebody doesn't know what a dot product is, they can put it in the Q&A and I'll answer it, but I'm assuming that everybody knows what a dot product is. And in a dot product, all you're doing is you're multiplying a particular row with a column. In this case, we have just one column, which is the weights. So the result that we're going to get is going to be, in fact, I can show it. It's going to be 506 by 1. And that's going to be a prediction for every single data point. So this is one, in fact, if I cut it down, it's 8 lines of code. I was able to do the same thing using just one line of code, but beyond that, it took 1.29 milliseconds, while this took 67.8 milliseconds. And keep in mind, this is a very, very, very small data set to the point where it's only 506 values. And the difference is almost a factor of 60. If we were to explode this to 10,000 data points, and the difference is a factor of 60, then you can start to imagine that things start to get very, very complicated. So again, the goal over here is, number one, to understand how this vectorization helps. And the way that it helps is that when we convert for loops to simple linear algebra dot products, in that case, not only is our code more concise, but we're also running our code in a much more efficient manner, because all of this is handled by NumPy, and NumPy at the back end is written in C++, and it has a lot of parallelization that goes on as well. So all of this is done almost instantaneously as compared to you actually going over every single value in a for loop. So this is the first aspect, which is the vectorization aspect of it.
Hey, awesome. We have
Um,
a couple of questions.
yes.
Um,
Okay.
one is, can you go over the dot product really quick?
Okay. Sure. I can definitely do that. So what happens in the dot product is essentially what's happening in this for loop. Um, if I have a small data, let's say small x is equal to, and I'm going to create a small data set over here. In fact, I think I did over here. Yeah. So I have A and I have B. If I were to look at A, it's 1, 2, 3, 4. If I were to look at B, it's, in fact, let's change B. B is equal to np.array 2, 2, 2, 3, 5, 6. And then if I were to look at B, it's 2, 3, 5, 6. What's happening over here is that if I were to go and do this, how did we get this value 12? The way we got this value 12 was we took the first row of A, which is 1, into, and we multiplied it with the first column of B. So that's 1 into 2 plus 2 into 5. Ah, my bad. 2 into 5. So we got 12 over here. And that's how we got the first value over here. The second value over here is going to be, where's A, where's B? This is A, and this is B. So we have the first row multiplied by the second column. So we have 1 into 3 plus 2 into 6. So I'll just make this a little bigger so it's easier to see. And yeah, first row multiplied by the first column and we get 12. First row multiplied by the second column and we get 15. And we can do this. Second row multiplied by the first column is going to be 3 into 2 plus 4 into 5. Second row multiplied by the second column is going to be 3 into 3 multiplied by 3 into 3 plus 4 into 6. And that's how we get this matrix over here. And this is the simplest form of a dot product. All you're doing is multiplying each row with each column and summing the values. And that's essentially what a dot product is. So what are we doing over here? If we were to inspect this for loop properly, let's take a step back and let's just look at one row of the data. So if I were to take out one row of the data, which is simply going to be small x, is going to be x0. And if I were to look at the shape of x, it's simply 13 by 1. And if I want to get one prediction, which is what this function is showing over here, I would go over each weight for theta, data point in zip weights x, then I'm simply multiplying theta into the data point, and I'm adding those values. One prediction is equal to 0, and I'm adding those values together. So what did I do over here? If I were to inspect x, and if I were to inspect the weights, we're multiplying one with this, then one with this, then one with 2.3, then one with 0.0, then one with 5.38, and we're adding it all together to get this. And this is done over every single data point. So this small x is one row of the data, and our weights array is an array where there's just one column, and each column, and this one column just has every single weight attached to it. So instead of going over each data point and calculating this manually, we were able to take a shortcut and then simply apply this to the dot product over here. So, okay. Now, does that answer your question about the dot product over here? If somebody can just say a yes or a no, I can move on, because unless you understand the dot product, then there's really no point. Again, all we're doing is we're multiplying each row with each column, and that's all we're doing. And because we're doing that, each row in the data is an entire data point or an entire row. And then when we multiply it one by one, we can just simply do that with a singular dot product. And what this dot product is doing is taking each row of x, multiplying it with the column, which in this case, there's only one column, which is all of the weights, and it's putting it into one array, and that's it over here. One trick that I'll tell you with a dot product is that whenever you have array 1 at array 2, the result resulting array will have the shape of array 1 dot shape 1 by array 2 dot shape 0. So let's see this. What is x dot shape 1? It's 13. Sorry. Yeah. 0. Yeah, that's the rule. The rule is that when we're doing array 1 at array 2 or array 1 dot array 2, then the resulting shape, and this is a main trick that I use all the time. If we're multiplying x with weights, or we're taking a dot product between x and weights, the resulting array will have shape 506 by 1. So we take the number of rows of the first array, because that's what we're doing. We're multiplying each row with each column, and we get the number of columns in the second array. This is a trick that I use all the time. In fact, in most cases, if I'm just able to figure out the shapes, then half of my problem is solved. So now that we understand this properly, let's just move on. And before that, I'll take any questions. So we have some slightly irrelevant questions. Why is Relu better than Sigmoid? That's a good question. It takes a little bit of time to answer. In a nutshell, it's because with Relu, you're not just stuck between 1 and -1, but you're also able to go all the way till infinity technically when it comes to positive. So you have a lot more room to play, but it also has problems, which is why we use leaky Relu. And we take harmonic mean in F1 score. Why not AM or GM? I'm assuming AM means average mean, I'm not sure. And well, the reason is because with the harmonic mean, we want to balance precision and recall, and we can do that. Again, I would like if the questions are a little more relevant, but let's move on. Okay, so yeah, in object, or now let's move on to the second concept that we'll be using a lot, which is object-oriented programming. And object-oriented programming is a very, very complicated topic. There's entire university courses which are dedicated just to object-oriented programming. Over here, I'll only be teaching you the basics, and mostly because in Python there's a lot of things that exist in object-oriented programming that don't exist in Python. If somebody knows about it, then if the term private and public variables rings a bell, then you would notice that in Python there's no such thing as a private and public variable. But the simple thing is that a class is just a thing that, or a sort of blueprint that you define. And once you define that blueprint, then you can create objects of that type. So for example, over here, I've created a class dog. The syntax is simply class dog. And every class should have a sort of init function. And this init function is a sort of automatic function, which is written with double underscore init and then double underscore afterwards. And this is run automatically, in which you can pass some variables to it. And once you create those variables, you can create what are called attributes. These attributes are things or variables that exist within the class. And then you have certain methods. Methods is just a fancy way to say a function that exists within the class. And using this self variable, that function has access to the attributes within the class. So what do we have? We have attributes that are simply variables that exist within the class. And then you have methods that are functions that exist within the class. And using the self syntax, you can access those attributes within the class as well. So what have I done over here? I've created a class. I've created one function called def, in which I've assigned these variables to it. And just by the way, they don't need to be assigned anywhere. They can be assigned anywhere within the class as well. So I can just say self.species is equal to unknown. And then whenever the class dog is instantiated, i.e., whenever we create an object, let's say I've created an object called dog. Sorry. I've passed it the parameters Tony and 10, which means that this is a dog whose name is Tony and their age is 10. Why? Because now self.name is equal to name and self.age is equal to age. Then when I print the attributes, then species is there. Because even though I didn't initialize it directly, because outside the function I have this variable, and because these methods can access these variables using self, then I can simply do it. And if I were to ignore this, then I might get an error that dog object has no attribute called species. And that's exactly what we're doing here. It's just a way to package things in a nice way that we can reuse again and again. And similarly, in Python, there's no such thing as a private variable. Ideally, we would want some sort of control over these attributes so that we cannot change them outside the class. But in Python, you can do that easily. So I've changed the dog's name from Tony to Ezekiel. And now if I were to print the attributes, their name is Ezekiel. So there's a lot of attributes that can exist within class. In fact, when we were to call the sklearn function, if we want to know all of the attributes that exist within sklearn, so for example, let me just, I'm going to sklearn a random adabuse classifier. I'm going to import this. And suppose that I want to see what attributes exist within the adabuse classifier. I'm going to use an inbuilt variable called dir. And I can see that there's a lot of things over here. And to compare, I'm going to compare it with my own class that I created, which is dog. And within dog, I have all of these different things that I didn't really initialize, but they're somehow still there. That's because there are some things that classes need when they're built in the first place. And for that, we have all of these different variables. Some of these are very useful. So for example, this dict variable, I can simply print all of the attributes of dog in a dict. And that's something that's very cool. So yes, if we were to try and look at this, then up till here, all of these things are standard Python things. But then we can see that, okay, this has a boost variable attribute, this has a boost discrete attribute. And in Python, the naming convention is that when you have a single trailing underscore, then that means that this is only supposed to be used internally. You obviously can access it outside of Python, but usually this is used internally. So check end features, compute probability from decision. These are all things that Scikit-Learn is using to create and run the AdaBoost classifier. However, these are all things that we have access to. So everybody knows the dot fit function, everybody knows the get params function, everybody knows the predict function. And without even looking at the documentation, which of course you should do, you can use the dir function to access all of these attributes. Because at the end of the day, all of these scikit-learn libraries that we get, they are classes, and they're multiple nested classes, which again is very complicated. We won't be getting into that, but it should give you a good primer to be able to at least look at the source code of scikit-learn and figure out how they're doing things if we ever run into problems. Now, one small thing over here is that there's a lot of scikit-learn functions that we can use without instantiating a class. So right now, if I wanted to print the attributes of dog, I couldn't just do dog.print attributes, because this would give me an error, because it's saying it's requiring one positional argument self, but I didn't pass any argument when I ran it here. It still worked. Why? Because I instantiated an object out of it. So in object-oriented programming, there's two things. The first thing is that you instantiate a class, and the second thing is that you create a class, which is a blueprint, and then you create an object from that class, which is the actual object that contains the values for that particular blueprint. And once we have that there, that is what is passed in this self variable automatically. So now that we have all of the basics set, I want you guys to strap yourselves in, because this is about to get very, very complicated, very, very fast. Just one last thing, that we have these things called static variables. And static variables are variables that we can use without necessarily instantiating an object. So I've created a class called random functions, and without even creating an object, I can call this function. So I didn't create any object, I didn't do anything. I simply called this function and it printed hello world. This default method is what's called an instance method. And I can't run this because I need to first create an object. Once I create an object, then I can run it. And I just printed self, and it's telling me that self is a random functions object. So yeah, now that we have the basic set, and this static method is, by the way, how we're able to use things like train test split, because technically train test split is also a part of a class in scikit-learn. But because it is a static method, we can simply use it without any scikit-learn object. So there's many other, I've attached this link over here that you can open if you want to learn more about object-oriented programming, but we're going to be skipping that part. Now, let's get into it. Does anybody have any questions? Because again, I would like to say that this is going to get very complicated very, very quickly. So if anybody has any questions, now is the time to ask. And I'm going to wait 10 seconds. Okay, let's get started. So as a primer, what is the gradient descent process? The gradient descent, and I'm not going to be talking about it intuitively because there's plenty of resources. If you were to Google how to do gradient descent, you're going to get extremely cool animations, visualizations about how there's a ball rolling down a hill, all of these things that are very good if you want to understand gradient descent intuitively. But our goal over here is to convert the gradient descent functions into mathematical formulas. So gradient descent is essentially just a two-step process that's repeated over and over and over again. The first step is that you calculate the derivative of the loss function with respect to each weight. Let's take a step back here. The first thing is a loss function, and that can be anything that defines how good or bad your model is doing. You calculate the derivative of the loss function with respect to each weight, i.e., you calculate the partial derivative, and then you update each weight accordingly. So what is the equation of the mean squared error? The mean squared error is a very, very basic error that we use in linear regression all the time. And all we have is that we have yi. So whenever there's I to n, that means that for each data point, the error is going to be different. So for each data point, we take the true value of y minus the predicted value of y, which is always going to be y hat. And y hat is the same as our hypothesis function above. So all we have is weight 0 multiplied by x0 plus weight 1 multiplied by x1 all the way till weight m multiplied by xm, where m is our number of features and n is our number of data points. So again, what are we doing over here? We're taking the difference between the true value and the predicted value, we're squaring it, and then we're taking the sum. So this summation can be done using a for loop, whereby we simply go for data for true value prediction in zip y pred, and then we simply just total is equal to 0, total is equal to true value minus prediction, and then we would square it up. And then at the end, we would divide total by the len of y, right? This is the for loop way of doing it. But why are we creating a for loop when we know how to do vectorized operations? And in NumPy, it's as simple as finding the difference between the two arrays. Because if you recall, as I showed you, finding the difference between two arrays is going to subtract each individual value with each other. Then we square it, which is going to square each individual value. And then we just take the mean. And why am I taking the mean? Because, well, if you notice, then what is this doing? This is summing all of the values and then dividing it by n. That's simply the mean. So we can create two sample arrays. We pass it to our sample MSE function, and we get this error. And it makes sense because all of these are correct except for one. So the error is 0.25. Now, let's have a look at what the derivative of the mean squared error looks like. And this is a little more complicated. And I'm not going to show you the derivation of this derivative. If you're interested, again, I've showed this link. My goal here is not to teach you calculus. I'm not even that good at teaching calculus. So we're going to focus on the coding aspect of it. So just take it as it is. The derivative of this function over here is going to be minus 2xij. So it's always going to be for a particular weight. So for weight number j, the derivative is going to be minus 2xij, and then simply the difference between the true value and the predicted value. So for each weight, we are multiplying the data point associated with that weight. And the difference is that, and we're multiplying it with the difference between our true value and the real value. Again, this sounds awful lot like a dot product, because over here, we're multiplying each row with each column. So if our X is a data set of shape n by m, where we have n data points and m features, our Y values are going to be of size n1. and our weights are going to be of size m by 1. That means the partial derivative that we want, because remember, in a linear regression, the weight update equation is such that each weight is updated by its own partial derivative. So if we have an array of weights, that means we also have an array of partial derivatives, and the shape of that partial derivative is going to be m by 1. And this is what gives us our first hint. What hint does this give us? The hint that this gives us is that when we do this calculation for all of the weights together, again, because we want to do this efficiently, we don't want to run a for loop over each and every weight and then calculate the partial derivative one by one. We want to do this for all of the weights together. The result of the partial derivative is going to be m by 1, the same as our weights, so that we can simply subtract them. The second thing we should notice is that for a particular weight, only the relevant data point is multiplied by the value of the difference. And let's have a look at this. Now we have a slightly more complicated data. I mean, it's still a toy data, but it has 3 features and 4 data points. If we want to initialize the weights, then take a second to guess, but our weights are going to be of length 3 because we have 3 features over here and 4 data points. Again, it's going to be x dot shape 1 by 1. If we were to get our predictions just as before, it's x at weights. Our predictions are of size 4 by 1 because for each data point, we're going to have one prediction. And I've randomly selected some predicted values. So they're off by just a little. The first value is supposed to be 1. I've set it to be 8. The second value is supposed to be 6. I've set it to be 7, and so on. Now, if we were to calculate the loss over here, let's get that loss. It's 1.0. So for this particular data, the loss is 1.0. So now let's actually implement this function. The first step is to find the difference between the true values and the predicted values. The difference is of shape 4 by 1. Our x is of shape 4 by 3. The resulting partial derivative that we want should be of shape 3 by 1. Something doesn't make sense over here. How do we do this? What we want to do is that we want to multiply the entire first column with the difference. So if this is x, and let me just remove these two. What we want to do is I want to multiply this with this, then multiply the second row first column with this. And instead of multiplying the rows with the columns, I want to multiply the columns with the columns. That doesn't sound directly like a dot product, but if I were to simply take a transpose, I can do it like this. So I've taken a transpose, in which case this column has now become the row, and now I can simply do a dot product. So minus x dot t at the difference, and now the partial derivative is of shape 3, 1. The 0 and 1 value of the MSE you calculated, what is this 0 and 1 representing? So it's not necessary for it to be 1. In fact, if I were to change this value a bit more, the value is going to increase to 3.0. All this is doing is that it's finding the difference between my actual value and my predicted value. It's squaring it, and then it's finding the mean of it. So what we're doing is we're finding the mean squared difference, or the mean squared error between our actual value and the predicted value. And that is essentially a measure of how good or bad our model is. There's many different ways to calculate this error. Mean squared error is just one of them. Some people are more aware with the root mean squared error, but I didn't use that here because the derivative is a little more complicated. But essentially, that's all we're doing. Um, these, in terms of what they represent, that's a good question, because it's a little difficult for me to say that 1 is a good error, but 10 is not a good error. That generally depends on the data point, and that's why, and it depends on the problem at hand. So that's an entire other topic on how you evaluate regression models, and I don't want to get into that right now. But very easily we were able to calculate this. Let me just do it again, because I think I updated my weights too much. So just to run it again, we have X, we have these weights. I created a Y true randomly based on my predictions. Then I found the difference, and I found that the error right now is 1.0. Then I calculated the partial derivative, and then I did the weight update. So when we're doing a weight update, we want to multiply a learning rate. And again, intuitively speaking, this is so that our weights don't get updated too drastically too many times, because then we could overshoot and not actually get to the optimal value of the weight. Um, but if you know this intuitively, this should not be big of a problem to understand. And we updated our weights, and we saw that just by running this epoch once, our weights got better by 0.05. And I can do this again and again, and it'll get even easier. So in just one iteration, we reduce our loss from 1.0 to 0.95. And then all I need to do is run these cells again and again, and we will get to the same response. So I'm going to show you one more loss function, and then we'll actually start coding up the class. So another popular loss function is what's called the mean absolute error function. And in the mean absolute error, instead of squaring the difference, you're just taking the absolute value of the difference, and then you're taking the mean of it. But the derivative of the absolute function is not straightforward. If I were to go into the mathematical complexity of it, it's because if I were to try and graph this value, it would be like a V. And because of that, the mean absolute error function is not differentiable when y true is the same as y predicted. However, we can, in most cases, it is approximated as a stepwise function. So this I've broken down into a chain rule. And what the chain rule is doing is that to find the partial derivative of the error with respect to weight j, you take the derivative of the error with respect to the predicted value, and then you take the partial derivative of the predicted value with respect to weight j. This is simply going to be xj. Why? Because yi is equal to w naught plus x naught plus w1 plus x1. So for a particular weight, we're only interested in that particular value. So for weight naught, the derivative is simply going to be x naught. So this part is simple, but how do you take the derivative of the absolute function? And that's a stepwise function. Simply put, if the predicted value is greater than the actual value, your differential is going to be +1. If it's less than the actual value, your differential is going to be -1. So a very interesting difference between the absolute value function, between the absolute error and the squared error is that in the squared error, the magnitude of the difference also matters. But in the absolute error, the magnitude of the difference doesn't matter, only the direction matters. So if in a problem, for a particular problem, our predicted value is way off from our actual value, then the squared error might actually work faster than the absolute error, because the squared error is taking that magnitude into account, but the absolute error is not. That's just a small side note. Don't get too hung up on it. And this is what the differential looks like. And the reason I want to talk about the absolute error is because in a lot of cases we do find stepwise functions in maths as well. And when we want to apply stepwise functions to a programming language such as Python, it sounds daunting, but it's actually much easier said than done. So again, if we were to find the sample mean absolute error, it's simply going to be y minus y pred, and this can be a single number or this can be an entire numpy array, and it will work just as fine. We find the difference, we take the absolute value, we find the mean, and we return it. It's as simple as that. But one very important function in NumPy is called the np.where function. In this, the first parameter is your condition. The second parameter is the value that return value to return if condition is true. And this third parameter is the value to return if the condition is false. So I've created a small array 1, 2, 3, 4, 5, and I've said that if the value of a is less than 3, then the value should be 0. Otherwise, the value should be a. And I can run this and you can see that the first two have become 0 and the rest of the 3 have remained the same because I've said just keep the same value. And I can do this anyway. So I can say take the exponent raised to the power 10. And this has become 1, 10, 0, 2, 4. I can say multiply it by 10 and this has become 10, 20. And I can put values. So I can either use the same array. I can even use a different array as long as it's the same length. So if I do this, 10, this is also 5 values. I can just do this as well. As long as the length is the same, it will work. So how do we get the derivative of this? The first thing we do is that we find the difference. Why do we find the difference? Because instead of it would be much more complicated to try and whip up an if statement to do this directly. So we use some clever mathematics. We find the difference. And in mathematics, you can say that, oh, it's not defined at y hat is equal to y. But in programming, we can't do that. Like, what do you mean not defined? I'm I'm running a program. I need to define it. Something has to happen if that scenario were to come up in the real world. That's not an assumption. That's an assumption I can make as a mathematician, but that's not an assumption that I can make as a programmer, because there will be some edge case in which y hat is equal to y. And if that edge case does end up coming about, what do we do? Intuitively speaking, I would ask you guys to think about this for a couple of seconds. Intuitively speaking, if the prediction is perfect, what should we do? In fact, I want somebody to answer this in chat. If our prediction is the same as our actual value, what should the error be? Should it be +1? Should it be -1? Should it be something else entirely? So if anybody can take a crack at this in the chat. Yes, so Nisha server says it should be 0. And yeah, that's pretty much the correct answer. If our prediction is perfect, then we don't want anything to update. If we don't want anything to update, then our partial derivative, which is what updates the weights, that partial derivative should be 0. And in this case, that's precisely what we're going to do. If the difference is 0, then we substitute the values with 0. Otherwise, we just take the difference as it is. If the difference is positive, then we substitute it with 1 and we keep the other value as it is. If the difference is negative, then we take the negative value and keep the rest as it is. What does difference being? So again, remember, I'm taking the difference between prediction minus the true value. So if the prediction is greater than the true value, then this difference is going to be positive. If the prediction is less than the true value, then this prediction is going to be negative. So what do? I take this absolute, I run the same differential that I ran before because I know it works. And then I do the same process that I did before. I create some random toy data where this is what the difference is. I calculate the absolute error. I calculate the partial derivative. And then when I update the weight, the partial derivative has gone down a bit. And I can keep running this again and again. And we'll get closer and closer. And this should already start to make sense. Very simply, what we've done is that we have created a simple partial derivative function that we can run again and again and again and again. And slowly, our weights will start to converge to a point where they are optimized enough to give us the right answer. So now let's actually start to write up this class. So what do we need for this class? The first thing we need is an initialization function that takes in all the important values. So we have def in it, and it's always going to have self in it. And let's say that I want to be able to, let's keep the most simple kind of linear regression that only uses one loss function, which is the mean squared error. What do I need to define for that? I need to define the max number of iterations that I'm going to run, whether I want to run 1,000, whether I want to run this 1,000 times, or I want to run this 100 times, or whatever. And I need to define a learning rate. This is the most essential things. And what I'm doing over here is that I'm giving it some default values such that even if a person doesn't define the values, there's going to be some default values for it. Then I'm going to define some weights. So self.weights, initially they're going to be none. Why? Because we can only define our weights when we know the shape of our actual data. Remember, the weights have to be the same size as the number of features, so we cannot define it right now. We're going to say that our self.max iterations is the same as max iter. We're going to say that our self.learning rate is the same as, and again, as the learning rate that we pass into it. So this is the very basic initialization that we need to run our actual model. What's the next thing that we need? The next thing we'll need is some way to initialize the weights. Okay. So we have a number of features that get passed into it. And initially I initialize it as 1, but it is good practice to use a normal distribution with mean 0 for weight initialization. Again, there is a lot of research on the best way to do weight initialization. And there's things like the Xavier initialization method. There's one created by Hu et al. And we're going to be sticking to the simplest form, which is np.random.normal. And the size is going to be the number of features, comma 1. So now we have our two main things set. We have a way to initialize our weights, and we have a way to initialize the class itself. Now, the next thing we need is a predict function. What does this predict function do? What this predict function does is that it takes a self, it takes an X, which could be any data set, it could be a test data set. We say that the Y pred is equal to X at self.weights, as we were doing before. And then we simply return Y pred. Now let's get to the difficult function, which is the fit function. What are we going to pass into the fit function? We're going to be passing self, which is the object itself. We're going to pass an X, and we're going to pass a Y. The first thing that we're going to do is we're going to, just to be sure, as a sort of error handling, we're going to make sure that the length of X and Y are correct. So we're going to assert this, and if this is not true, then we're going to raise an error, and we're going to say that X and Y should be the same length. And then once we do that, we're going to initialize the weights. So we're going to call the function self.initWeights, and we're going to pass it x.shape1. We've done this before, we're just only putting it together. And now we actually get into the actual gradient descent. We're going to run for dash in range self.max iter. And the reason I've put a dash over here is because I don't need a counter variable here. If you do, then you can add an I over here, but I don't really need it. The first thing I'm going to do is that I'm going to get a prediction, because this is what we'll do to calculate our loss. So use X to predict the particular prediction. Then we're going to carry out our loss. And for now, I'm going to leave this empty, right? And this is a very important thing that we often forget in programming, is the idea of abstraction, which is the idea that I can either take a bottom-up approach where I define every single small function before I define my big functions, but then I lose sight of what I'm trying to do. So before I actually define the loss function, I'm just going to assume that I've created a loss function over here. I'm just going to say get loss. I haven't defined this yet, but I know that I have to do this. Okay, so that's the first thing done. The second thing we're going to do is we're going to find the partial derivative. So how do we find the partial derivative? Again, we haven't done this yet. Get partial derivative from function. And we're going to define these functions, but right now we're going to leave it as it is. Then we're going to update our weights. And we're going to say self.learning rate multiplied by the partial derivative that we get. And this will update our weight. So right now we have a very simple dot fit function that does it in 3 steps. But this isn't enough, because we want some way to be able to monitor what's happening and how we're doing it. So I'm going to add a couple of more details before we start writing up the loss functions. And I want to store my loss history. And for that, every time I calculate the loss, I'm going to say loss history dot append loss. This way I can get the history and figure out if my model is even working fine or not. Another thing that I'm going to do, and this is something that's very interesting, is, in fact, I will get to that later. Let's just run this once and let's start writing up the loss functions. So let's say that we have the main loss function, which is mean squared loss, which takes y pred. And as before, I'm going to return np.mean y minus y pred into 2. And this should be a static method, because I should be able to calculate my loss regardless of whether I have a linear regression model or not. This should work regardless of anything else. But the derivative is something that will only be used internally. So self x y pred, and then I'm going to return minus x dot t at y minus y pred, and this is something we did before. And then we're going to divide it by len x. It would be a good idea to wrap this in brackets as well. So now we have this. So now we can do this easily. Self dot mean squared loss y pred. Partial derivative is going to be self dot mean squared loss derivative x y pred. Let's see if this works. Okay, and just for now, what I'm going to do is I'm going to print the loss function so we can monitor what's happening. And I'm doing some basic pre-processing over here where I'm scaling the data. And especially when you do this manually, this is essential to do. In fact, in Scikit-Learn, they do some sort of scaling within the linear regression class, but we're just going to do this outside. All this does is that it centers it around a mean of 0 and a standard deviation of 1. So if I were to create this regressor, got unword, okay, let's remove this for now. Input 1 does not have enough dimensions. So clearly I've made an error over here. Let's check it out. So we're getting an error here and we're getting an error. How do we figure out what this error is? We print out x.shape and we print out self.widths. None type object. So clearly I did self.init weights. So there's an error here. See? And the only way I was able to do this was because I looked at the shapes. Just by the way, I'm coding this actually live. So I'm going to be running into problems. And now you can see very clearly that our loss is decreasing. I mean, it's decreasing very slowly, but it's working. So we're actually getting somewhere. Now let's start to add a bit more complications into this, okay? So what we want to be able to do is that we don't always want to run 1,000 uh, iterations. We want to be able to stop early on as well. So if I were to change the learning rate to something like 0.01, then, okay, even this is not very quick. You can see over here that even though the loss is a lot, the learning rate is not changing at all. In fact, from this point onwards, after every 10 iterations, it's only decreasing 0.000001. And that's a little stupid, isn't it? Because why are we keeping on running our algorithm when it's clearly reached an almost optimal value? So for that, we're going to add one more thing into this, and that's what's called the tolerance. And we're going to say that the tolerance is something like 0.0001. We're going to say self.tolerance is equal to tolerance. And then within the fit function, what we are going to do is we're going to say if after we've calculated the loss, if np.absolute loss minus previous loss, what is previous loss? We haven't defined it yet, but don't worry, is less than the self.tolerance. So remember, it will never be exactly the same, but if the difference is smaller than a very, very small value, then we can simply say that the model has converged and we will break. And we can initially we can say that the previous loss is going to be infinite, because before we do anything, the loss is infinite, and that is what np.infinite does. And at the end of it, so at the end of our predict function, we can say that if the model has converged, we'll simply print model converged, else we'll print warning max iterations reached, model did not converge. So slowly and gradually, we're able to add more and more complications into our class. And if I run this again, converge reference before assignment. Why? Because I have not said that converged has to be false. Max iterations reached, model did not converge. And if I were to change the tolerance over here, we'll notice that it will change. Okay, so this again isn't working. Interesting. Let's find out what the error is. Maybe our loss function isn't working. This is going to take a while. I know what I'm doing wrong. I have said that previous loss is infinite, but I am not updating it. So previous loss is equal to loss. Cool. And now we can check it out. And after printing, it said model has converged. So now we're actually getting somewhere, which is pretty cool, to be honest. Okay, so let's slowly and gradually start to add even more complications into this. So another complication that I want to add is that we want to be able to have some sort of fit intercept as well. So if you remember in linear regression, we have that weight update equation, but we can also introduce a bias. That bias in scikit-learn is called fit intercept. And this is either going to be true or false. And now would be a good idea to fit intercept. By default, it's going to be true, right? So if the fit intercept is true, then instead of adding a separate bias term, which would require its own derivative and brings up its own host of problems, a very simple way to implement this is we take this fit intercept. If it's true, which by default it is, then we just np.concatenate. We take x, we take np.ones of shape is equal to len x by 1. So we're just appending another column to it. And then we say axis is equal to 1. So now we've simply added a fit intercept to it by almost no problem at all. Okay, so one more complication added. Let's check it out. And see, just by adding the fit intercept, my loss got so much better. And that's because it gave my model that much room. And see, once you start to implement these things by hand from scratch is when you start to figure out how important very, very small things can make. All I did was add a fit intercept and my model was able to converge from 572 to 29 because I allowed the line to move um, above and down. So there's a question, are there some types of data spread where it won't converge? Yes, definitely. Like that entirely depends on your data. There's definitely that definitely might not converge at all. And that is why there's always a trade-off between number of iterations, learning rate, and your tolerance. I should probably increase the tolerance a little bit. But if I were to reduce the tolerance, then I'm pretty sure my model will not converge. Oh, it's still converged because I have a lot of iterations. Let's keep it to 1,000 iterations. And it's still converged. Wow, my model is too good. I can't do anything about it. So, okay. Now let's add the last complication because we have 10 minutes left. So suppose I want to be able to pick and choose which loss function I want to use. So I can add a simple, and the way that scikit-learn does it, if you remember, is that you add a simple string to it in which you say that you want to use MSE or you want to use absolute, the absolute error function. And then we define those two functions. So we say at static method, uh, yeah. So at static method def mean absolute loss y widespread, return as we did before np.mean np.absolute y minus y spread. And then we remember the derivative, and I'm just going to copy paste the derivative because it's too much. And let's just clean it up a little bit. Okay, so now we have our absolute loss. So now the thing is that when we have multiple different loss functions, the two lines that are going to change is this line and this line. And a very simple thing we can do is that we can add a bunch of different if statements that if the something like um, if self dot, wait, did I add it to self? I don't remember. I did not. Self dot loss function is equal to loss function. So I can simply do something like if self dot loss function is equal to MSE, then do this. Elif self dot loss function is equal to MAE, then do the other thing. But I'm not going to do that. Why am I not going to do that? Because this will get very messy very, very fast. Imagine if you have 10 different loss functions. Are you really going to create 10 different if statements? That's not a very good idea. And now I'm going to start to go a little quickly because we're running short of time. A very cool thing you can do in Python, and which is why dictionaries are my favorite thing in Python, is that I can simply attach this string to a function. So I've already defined the function mean squared loss, and the key is the string, the value is the function. Absolute, or in fact, I'd rather say MAE, self dot mean absolute loss. Now what I can do is that over here, I'm calling a function. Which function am I calling? I don't know. I'm going to simply call the loss dictionary. Within the loss dictionary, I'm going to pass the value of loss function, which we have defined over here. And when I do that, it's simply going to replace it with this function to which we're passing these values. And this will also make sure that every new loss function that we make has the same format, whereby it takes the same input and returns the same output. And that's something that's very essential when you're trying to write scalable code. And we can do the same thing with our derivative dictionary. Self dot mean squared loss derivative. And now that we have this, all I need to do is change this to self dot derivative dict, self dot loss function. And I assure you, hopefully, it works just as fine. And now for one final complication. We talked about the loss history. Let's actually formalize it. Initially, it's going to be none. And then once we have the history, we're going to say self.loss history is equal to np.array. Converting into an array is always helpful. And another thing that I want to store is actually my weights as well, because I want to, for the last 5 minutes, I want to visualize how changing some things is going to change my model. So we have our weights history over here, and right after we calculate our weights, which is going to be here, right before we calculate our weights, dot append self dot weights, and this is going to give an error. So what reshape minus down one is that it flattens the array. Right now it's going to be a number of features by one array. In this case, what I want it to be is just 13, just a single one-dimensional array. So that's what we're doing over here. And because once again, NumPy arrays are objects, that means that if I were to keep appending it to a list, when it changes, it would keep changing because the only thing that's stored in a NumPy array is a reference to the object. And when I change the object, which I'm doing over here, even if it's stored in a list, it's going to get changed within that list as well. So what do we have to do? We have to call the copy function so that it creates a separate copy and then it passes it. And simply weights history is equal to np.array weights history. And I will finally create a function to return these. Def get training history self return self dot loss history. And lastly, one neat thing that's always useful is the get coefficients method, which is there in Scikit-Learn. If you guessed it, it's simply self.weights. So now let's run it, and wow. So that's the randomness of it. Sometimes it works and sometimes it doesn't. So because it converged early, even though our max iterations were 1,000, we have 874 values over here, and we can visualize the performance. We see that the training loss goes down, and the weights sort of try to find an optimal value over here. And over here, I'm only looking at one of the weights. I can easily change the score to look at a separate weight. I can even look at all of them together, but that's not a very good visualization. And you can see they all tend to go towards one value. And something very interesting that I want to show you guys over here is that if I were to use the absolute loss function, so loss function is equal to MAE. Hopefully I didn't make any error while I was copy pasting this. Can somebody guess what's happening over here? In fact, there's not enough time to guess. The training loss is going up and down and up and down and up and down. So the simplest solution to this is to reduce the learning rate. And now it converged in only 109 steps. And see, if you notice, for the absolute function, the weights are jumping about a lot. And the reason is precisely because the magnitude doesn't matter. When we were using the squared error function, then we could clearly see that it was a very smooth line. And that's because as we get closer to the point, as our predictions become more and more accurate, the magnitude decreases. But in an absolute function, the magnitude doesn't matter. So it doesn't matter how close or far we get, the partial differential equation is only dependent on the particular data point, which is why this is a lot more jittery as compared to the squared loss function. So I'm going to wrap it up now because I want to respect everybody else's time. um, the point of all of this is for you to actually dive deep into all of this coding at least once in your life as a data scientist, because once you do this once, you will figure out how very, very small things, such as including this fit intercept, create such a massive difference in our models. You get an in-depth look into how our models work, and once you've done this, I assure you that it will be that much easier for you to figure out the problems in your models, because you've done this once. You know exactly how the model works. It's like if you've built a car, then it's easier for you to diagnose what the problem in your car is. But if you've never built a car in your life, if you know nothing about the car and your car breaks down, you don't know how to fix it. So if you built the car just once, then you're able to fix any car later as well. And all of these resource links, we should have emailed them to you. The only thing that matters is this notebook. This notebook has all of the links within it. Hopefully, we'll convert it into a blog post, and this has also been recorded and it will be uploaded. So I'll just pass it over to Nathan, who can wrap it up.
Hey, thanks, Awesome, and thanks everyone for joining today. If you have any additional questions about this webinar or the notebook, we will be posting this and a recording on our YouTube channel as well as on our tutorial site and our blog. Feel free to leave a comment there and we'll make sure it gets passed on to Awesome. Awesome, thank you very much. I think everybody really enjoyed this. We do have another webinar coming up on May 12th titled Building Trustworthy AI Solutions. It's with David Frostley, a principal AI architect at Microsoft. I've posted the link in the chat, so if you're interested, go ahead and give it a click and see what it's all about. Again, thank you, Awesome. Thank you, everyone, for joining, and I hope you all have a great rest of your day.